We're going to talk about our last topic in Geometry Foundations, which is one of our last building blocks and is just what we get when we start putting some segments together. So that new thing is polygon. So a polygon is a closed plane figure which has two properties that go along with it. And these next two things is kind of a loaded definition. There's a lot to it, but we're going to break it down item by item and see exactly why all this is necessary. So number one is formed by three or more line segments called sides. And number two, each side intersects exactly two sides, one at each endpoint, so that no two sides with a common endpoint are collinear. So let us start from the beginning. A closed plane figure. So a closed plane figure just means that, well, this thing is completely contained within a plane. I don't need anything like bending out a plane, making a three-dimensional object. It's all contained in one plane and it's closed, so it's not open. What I mean by that is, something that would be closed would be like this triangle. Something that would be open would be something like this. So it necessarily has to be closed and within one plane. So these other two attributes make it a little more interesting. So it is formed by three or more line segments called sides. So it always has to be at least three sides. So why? Well, if I just have two sides like this, obviously there's no way of closing these two segments. There's no way of doing this, and so I need at least three to kind of enclose a space. So just two sides, or obviously just one side, will not cut it for me. So three or more line segments, and yeah, we call these sides. That's another important part. So that one's not too bad, but then the second part here, each side intersects exactly two sides, one at each endpoint, so that no two sides with a common endpoint are collinear. We'll just take this step by step. Each side intersects exactly two sides. So what we're trying to avoid is situations where I have segments that intersect multiple segments here. So here's an example of a shape that I have a few sides here that actually intersect more than just two other sides. So for example, we could look at this point right here. It's a point of issue because this segment here will intersect, well, 1, 2, 3, 4 different sides. And so this, as it's drawn, is not a polygon. That's what I'm trying to avoid here when I say that each side intersects exactly two sides. The next part says that one at each endpoint, meaning that another situation that I could have is something like, let's just go something like this. This is not a closed polygon. I have this thing sticking off here, which is no good because this segment up top, it's not met by this other segment at its endpoint, and so having this extension is no good either. So this is also not a polygon. And then so that no two sides with a common endpoint are collinear. So this last part here is a little bit tricky, but what I'm trying to do here is just emphasize the fact that, let's draw something basic like a triangle here. So I think most people would obviously look at this and say that there are only three sides, but what this last part is emphasizing is the fact that, well, what if I added another point right here, and I wanted to make the argument then that this actually has 1, 2, 3, 4 sides. And so how I avoid this situation is by saying that so that no two sides with a common endpoint are collinear, specifically when they have a common endpoint. And so this makes sure that this is just a three-sided shape. And then last but not least, we have this definition here for what a vertex is, and it's just the endpoint. And so I just refer to these as endpoints this whole time, but it's the endpoints of any of the sides of a polygon. So obviously this is a triangle. We know this name already, but if we wanted to refer to it by name, the way that we would do it is by using the letters in order, the points in order. So this would be A, B, C. Triangles actually have their special notation in front, so this would be triangle ABC. Or I could have something different like if I have this quadrilateral, which we're going to talk about here in a second, but this four-sided shape, I call it A, B, C, D, and as long as I name these in order, I can start however I want. So I can call this B, C, D, A if I wanted to. This is polygon B, C, D, A. And so I'll just name them by going through the vertices in order. I can start wherever I want, just as long as I go in order. So I can't go C, A, B, D, or something along those lines. Triangles are the only ones, except for, I guess, some special types of quadrilaterals that have a notation in front of it like this. So let's go and further find some classifications to talk about. So another way we can classify polygons is by calling them either convex or concave. And so what that means is a convex polygon is a polygon in which no line that contains a side of the polygon contains a point in the interior of the polygon. So it's a very rigorous definition. It's a good definition, so we want it that way. But maybe a little bit simpler put, not as rigorously, is that something like this, for example, would be a concave polygon, so not a convex polygon. And concave is kind of, they bend in on themselves like this. So if we look at this definition, then for convex, it's a polygon in which no line that contains a side of the polygon contains a point in the interior of the polygon. So what it means by that is any segment, so that's a side of my polygon, the line that contains it, because they're just a portion of the line, cannot also contain points that are on the inside of the polygon. So, for example, this polygon is concave because this line that contains one of the sides contains points that are on the inside of the polygon. However, if I have a shape that looks like this, for example, it'll be the case that any line that contains my sides here will not contain points on the inside. So this is convex. And then probably one of my favorite definitions in geometry is what concave means, and it's just that it's not convex. And we can name it this way, or we can use this definition, because these are two mutually exclusive groups. There's no overlap between them. There can't be something that's either convex or concave, and I can't have a polygon that's neither convex nor concave. Every polygon will be either convex or concave. So that's one way of classifying polygons. Another way is by talking about the measures of their sides and their angles. So equilateral, it's just a polygon that has all sides congruent, and then my equiangular polygons are polygons with all interior angles congruent. And I'm having trouble with drawing again. I don't know why. Oh, that's why, because I haven't selected it. There we go. And then a regular polygon would be a polygon that is both equilateral and equiangular. So probably the most commonly known one is, of course, this polygon here. We know this as a square. It's a type of quadrilateral. And so the way that we would mark this is that we would show that all four sides are congruent and that all four angles are congruent, and this would be a regular polygon. However, of course, I could have some polygons that are equilateral but not equiangular. For example, let's try a sketch, maybe a pentagon. We could have a pentagon, for example, that is equilateral but not equiangular. And then, of course, I can have a polygon that's equiangular but not equilateral. And so those polygons would not be regular. So these overlap each other a bit. And of course, I can have not just quadrilaterals, but any polygon that is none of these. So let's see. And then last but not least, actually naming the polygons. So when we talk about classifying polygons by the number of sides that they have, these are the naming conventions that we use. And so most of these you've probably already heard of. Triangle is an obvious one. Triangle is an obvious one. Quadrilateral, so we're looking at these roots here. So quad, meaning 4, penta, meaning 5, hex, 6, hept. This is probably the one that gets most commonly misnamed, but it's a heptagon for 7, hepta 7, octa is 8, nona is 9, deca is 10. We don't name 11 because we don't like 11. And then dodeca, so do 2, deca 10, so 12 sides. And anything past that would be what we call an n-gon. So what I mean by that is if a polygon has n sides, let's say it has 15 sides, what we refer to that then is by just calling it a 15-gon. Because obviously there are names that exist for all of the different shapes that can exist, but we won't know them. And so anything greater than 12, but also including 11, we just name by using the number dash and then gon. So that was a little bit about polygons. All of our information kind of is the basics, and it's also our last kind of foundational thing for geometry. So we're going to be taking all these topics and building off of them later into hopefully more interesting and maybe more challenging things.